Chemical reactions, part 1. Balancing equations. Making the number of atoms on the reactant side equal to the number of atoms on the product side. Let's start out with a discussion of counting atoms. Now, if you want to represent a single atom, we would represent that with the symbol. So here's an example. H is representative of one hydrogen atom. That's the symbol H. If we have more than one atom, we would represent that with a chemical formula. Here's an example. Molecular oxygen. The formula is O2. Now that means that we have 2 oxygen atoms and 1 molecule of O2. Now there's an unwritten 1 in front of that formula. Here's another example of a formula, H2O. That's representative of 2 hydrogen atoms because the 2 is next to the hydrogen. And notice that we have an unwritten 1 down at the bottom here. Numbers on the bottom are called subscripts. So unwritten 1 subscript means that we have 1 oxygen atom. And there's also an unwritten 1 in front of the whole formula. A number that comes in front of the entire formula is called a coefficient. So that's representative of 1 molecule of H2O. Here we have a formula H2SO4 with a coefficient of 3. That means we have 3 molecules of H2SO4. And to count the individual atoms, we take the coefficient, the number in front, multiplied by the subscripts, the numbers on the bottom. So 3 times 2 is 6 hydrogen atoms. 3 times 1, there's an unwritten 1 by S there for sulfur. So 3 times 1 is 3 sulfur atoms. And then finally, 3 times 4 is 12 oxygen atoms. So there are a whole lot of atoms that combine to make up these 3 molecules. And let's take a look at this example on the bottom. 2 NH4 taken twice, CO3. And pay attention to the way that that language works. When we have a polyatomic ion like NH4 in parentheses with a number on the outside, we say that that's NH4, give a little pause, taken twice. And that's the way that we indicate that there's parentheses around the NH4. Now, because we have a 2 coefficient, that means we have 2 of this entire molecule. That's ammonium carbonate. So we have 2 molecules of ammonium carbonate. And 2 coefficient times the 2 subscript outside the parentheses times the unwritten 1 by the N inside the parentheses gives us the number of N's. So once again, it's 2 times 2, that's 4. 4 times unwritten 1 is 4, so that's 4 nitrogen atoms. Let's do that for hydrogen. 2 times 2 is 4. 4 times 4 is 16. That's 16 hydrogen atoms. This 2 applies to everything throughout that formula. So 2 times the unwritten 1 by the C means that we have 2 carbon atoms. And 2 times 3 by the O means that we have 6 oxygen atoms. One other important point, because we're going to run into some of these, is that there are 7 elements that are naturally diatomic molecules. So they naturally bond to themselves and exist as 2 atom molecules. There are 2 ways to remember this, what these 7 elements are. One is to know the rule of 7. Go to element number 7 on the periodic table. Here I have that indicated with that atomic number 7. And then make the shape of a 7. You get N, O, F, Cl, Br, and I. Now that's 1, 2, 3, 4, 5, 6 elements so far. If we add element number 1, hydrogen, that makes 7 diatomic elements. Another way to remember the 7 diatomic elements is that you can spell out the word Hankelbrief. H2, O2, N2, Cl2, Br2, I2, and F2 are the 7 diatomic elements. So whenever you write those elements in a chemical reaction, we put the formula for the diatomic element in the reaction. Now, if that element belongs to a compound, of course, we're going to not automatically give it a 2 subscript. That's only when the element is all alone. All right, so let's talk about balancing equations. This is where we make the atoms of reactants equal to the atoms of products, and that's in keeping with the law of conservation of mass. Now remember that subscripts, the numbers that are on the bottom, define the chemical formula. They define the chemical identity, so you can't change subscripts. Coefficients, on the other hand, can be adjusted to balance the equation. The coefficients tell you how much of each chemical you have. So let's consider this reaction. It's a pretty common reaction. Hydrogen, H2, remember that's one of the 7 diatomics, and oxygen, O2, another one of those 7 diatomic elements, combine to form water, H2O. Now you'll notice that's not a balanced equation, and we can do that. We can figure that out with a little bit of bookkeeping. Unwritten coefficient of 1 times 2 means that we have 2 H's, represented by H2 on the left-hand side of the arrow, and on the right, coefficient of 1 that's not written times 2 subscript means we have 2 H's. So the H's are balanced. Let's check out the O's. 1, unwritten 1 times 2 is 2 O's, and unwritten 1 times 1 is 1 O. So you can see that the way it's written here, it's not a balanced equation. The oxygen atoms are not equal. To balance that equation, we can't just put a 2 here because it wouldn't be water anymore. H2O2 is actually hydrogen peroxide. Water and hydrogen peroxide are definitely not the same chemical. So you can't just change this by putting a 2 subscript. We can never change subscripts to balance equations. On the other hand, what we can do is change coefficients. If we put a 2 in front of H2, that'll be 2 times 2 or 4 hydrogens. And if we put a 2 in front of the H2O, that's 2 times 2 or 4 hydrogens. Now we have unwritten 1 coefficient times 2 subscripts, that's 2 oxygens, and 2 coefficient times unwritten 1 subscript is 2 oxygens. Notice we have 4 H's, 2 O's, and 2 O's. So now the equation is balanced. Now, what we're doing here is using a technique that's called balancing by inspection. It's basically trial and error. That being said, I think very much like when you do a jigsaw puzzle, there are some tricks that you can use to solve the puzzle a little bit more easily. You can look for the corners of a jigsaw puzzle and lay the corners out. You can compare the picture on the front of the puzzle box to the colors of the puzzle pieces and decide that, you know, if you have a landscape with blue sky and green grass, you put the blue puzzle pieces near the top where the sky would be and the green puzzle pieces down at the bottom where the grass would be. You would maybe look for puzzle pieces with flat ends, and then you know you have the sides of the puzzle. So there are some hints that we can use when balancing equations too. First thing is, make sure you count the atoms correctly. And to help you do that, you might want to write in 1s that are unwritten 1s for coefficients and subscripts, and you might want to add parentheses where appropriate. We'll talk about some examples in a little bit. You might want to do some bookkeeping, and you might have noticed I did a little bit of bookkeeping in that example where we were taking hydrogen and oxygen to produce water. Wherever possible, count polyatomic ions as if they're single chemicals. And again, we'll go through examples of all of these. I like to phrase it this way: 2 times 3 equals 6. In other words, you can factor prime number coefficients. In other words, multiply the coefficients that are prime numbers like 2 and 3 by each other to make 6 of each chemical on both sides. And you could do that with 4 and 5, or yeah, like if you have a prime number of 5 and of one chemical and on the left side and 4 of that chemical on the right side, you could multiply 4 and 5. You'll see some examples of what I mean there. Another hint I like to use is double the recipe, and this is specifically used when we have an odd number of oxygen atoms and there's an O2 molecule that's in the reaction. Be careful about using this too much. You should really be stingy about using that only in the situation that's described here, and we'll go through some examples. And then just make sure that you're persistent. Balancing equations, like doing a jigsaw puzzle, can be frustrating. And sometimes you get lucky and the pieces fit well together and the equation balances easily, and sometimes not. And also be creative. Look for solutions. Be a divergent thinker and try different things. Now, it should be noted that sometimes equations are balanced. Here's a chemical equation for the reaction ammonium acetate and potassium nitrate produces potassium acetate and ammonium nitrate. Notice I have the ions written out across the top. So we have the ammonium ion crisscrossed with the acetate ion, the potassium ion crisscrossed with the nitrate ion, and then we change the order of the ions here and get compounds that are different compounds on the product side. However, notice that if we write in parentheses and even put in the ones for the subscripts, I guess we really don't need parentheses around the K there. You can see that there's one of every chemical. Notice that I'm counting the polyatomic ion NH4 as if it's a single chemical. So we would say that one coefficient times one subscript is one NH4 on the left, and one coefficient times one subscript is one NH4 on the right. Notice how I'm doing my bookkeeping here. I'm trying to keep columns of elements below the compounds that they're coming from, and I'm going to make a new line for each thing that I'm counting. So I've counted the NH4s. Let's count the acetate, the C2H3O2s. So we have 1 times 1, or 1 acetate. And I'm not going to bother putting the charges by that. And then over here we have coefficient of 1 times subscript of 1, so 1 acetate. 1 times 1 is 1. Notice we have a coefficient of 1 times 1 subscript, so 1K. Starting a new chemical, so a new line. If you have line paper, that's easier. And 1 times 1 is 1K. And then 1 times 3 is 1 NO3. And 1 times 1 is 1 NO3. And 1 times 1 is 1 NO3. So there's just one of everything. That's already balanced. And sometimes that happens with reactions. So we don't have to change any coefficients at all. What I'm going to do is run through these 10 practice problems on this balancing equations review sheet right now. Now you might want to go through this slowly. You might want to fast forward to reactions that you wouldn't be able to balance on your own. I would suggest that you might want to take a look at these and just try to balance these quickly on your own and focus on the ones that gave you trouble. Just like a jigsaw puzzle, you want to do this as fast as you can and you know, as accurately as you can, of course. So I would say, you know, the hints that we talked about, use those if you need to. Let's go through these one by one. Here's the first one. Notice that we have 1 times 1, or 1 Ba on the left, and 1 times 3, 3 Bas on the right. Now, it's a good idea when you're balancing to use pencil because you're going to find that you will do some erasing. So I'll put a 3 coefficient in front of that chemical. Now that means we have 3 Bas. So now the Bas are equal on both sides. Let's move on. 3 times 2 is 6 Cls. And on the right we have 1 times 1, that's 1 Cl, right? 1 coefficient, 1 subscript. So if we put a 6 coefficient in there, 6 times 1 is 6 Cls. And if it helps you, put those 1s in there. Okay, so the Bas and the Cls are good. Let's move on. Next in order, moving to the arrow here, is Na. We have 1 coefficient times 3 subscripts, so that's 3 Nas. And on the right we have 6 times 1, 6 Nas. So let's make that equal by putting a 2 here. So 2 times 3 is 6 Nas, and 6 times 1 is 6 Nas. All right, now PO4 is a polyatomic ion on both sides, and it remains as PO4, so I'm going to put parentheses around that and a 1 subscript. So 2 times 1 is 2 PO4s, and 1 coefficient times 2 is 2 PO4s. So while it may be a little bit tedious sometimes to write the 1s in there or to put parentheses where you really don't need them, it's sometimes a good idea to make sure that you're counting correctly, and it sure makes it easier to make sure you've done this correctly. We have 3 Bas, 3 Bas, 6 Cls, 6 Cls, 6 Nas, 6 Nas, 2 PO4s, 2 PO4s. And you can go through and multiply out coefficients times subscripts and verify those numbers. The one nice thing about balancing equations is you should know when you have it balanced and when you don't, as long as you do good counting. Okay, let's try number 2. C2H2 is actually an organic compound. It's called acetylene. Remember that O2 is a diatomic element, so it automatically has the 2 there when it's all by itself as an element. Now, you might know that water is H2O, but we're going to write it as HOH. And we're going to do that because when water, even though it's a covalent compound and it exists as a molecule, when water is in chemical reactions, and it is forced to break up into ions sometimes in chemical reactions, it breaks up into the hydrogen ion, H1+, and the hydroxide ion, OH1-. So it's a good idea to write water as HOH when you're doing chemical reactions like this. And then if we crisscross C4+ and O2-, we get CO2. But this is another example of a compound that's actually a covalently bonded molecule. And it would only break up into C4+ and O2- if it were forced to break up into ions in a chemical reaction. All right, so let's balance this equation. We have 2 C's on the left, and we can put a 2 in front of this, so we have 2 C's on the right, right? Coefficient of 1 times 2 is 2 C's, and coefficient of 2 times 1 subscript is 2 C's. Then 1 times 2 is 2 H's. And notice we have coefficient of 1 times subscript of 1 for this H, and coefficient of 1 times subscript of 1 again for this H. So if we have 1 and 1, that's 2 H's. We would add those together. Again, 1 times 1 is 1H, 1 times 1 is 1H again, that's 2 H's total. So the C's and the H's are balanced. Let's take care of the O's. On the left we have 1 times 2, so 2 O's. And on the right, and it's very important when you have elements written in more than one spot like we have with the oxygens. And oxygen is a pretty pervasive element. It's in the atmosphere all around our Earth, and it's very reactive, so we see oxygen in a lot of compounds. So that means in a lot of chemical reactions, we're going to see oxygen spread out throughout the reactant side or the product side. Make sure that you do bookkeeping when you have oxygens or any other elements that are all spread out like this. The bookkeeping like I'm doing down here. So 1 times 1 is 1 oxygen in the water, and 2 times 2 is 4 oxygens in the CO2. Now we're going to add these together, so we have 5 oxygens all together on the right. Now this is an example of where we would want to double the recipe, because any whole number times 2 is going to be even, and 1 plus 4 is 5. That's odd. So how are we going to put a whole number there, multiply it by 2, and get an odd number? That's not going to happen. What we can do is double the recipe to make our odd number of oxygens here even, because anytime that you double an odd number, you get an even number. So let's go ahead and do that. Let's make this a 2 coefficient and make this a 4 coefficient. So I just doubled those numbers. So now let's go ahead and recount. We have 2 times 1 and 2 times 1 again, that's 4 hydrogens. We need to make sure we have 4 hydrogens here. So let's put a 2 coefficient. We're going to take that 1 and multiply it by 2, so 1 times 2 is 2 coefficient. So now we have 2 times 2 is 4 hydrogens. Notice that we have 2 times 1, that's 2 oxygens, and 4 times 2 is 8 oxygens. And notice that we also did 4 times 1, that's 4 carbons. So we have to go back here and fix those carbons. 2 times 2, that's 4 carbons. Okay, so just to be clear, 2 times 2 is 4 carbons, 4 times 1 is 4 carbons. 2 times 2 is 4 hydrogens. 2 times 1 and 2 times 1 again is 4 hydrogens. And on the right, we now have 2 times 1, 2 oxygens in the water, and 4 times 2, 8 oxygens in the CO2, the carbon dioxide. Now 2 plus 8, remember we have to add these 2 chemicals, so we're adding the oxygens here. 2 plus 8 is 10. So what coefficient times 2 is going to give us 10? Well, that's going to be a 5. So now we have 10 oxygens. So these are the correct coefficients when the equation is balanced: 2, 5, 2, and 4. And that ratio of coefficients is something that we can sometimes have as a larger value or a larger ratio. You might have like 4, 10, 4, and 8. Now, if you can reduce the ratio of coefficients to the lowest whole number ratio, you should do that. The balanced equation should always be expressed with the lowest whole number ratio of coefficients. So 4, 10, 4, and 8 would be technically incorrect in terms of the balanced equation. We should be representing that ratio as 2, 5, 2, and 4. Again, if you can look at the ratio and divide it by the same number so that it can be reduced, you should do that to get the correct balanced equation. Okay, moving on to problem number 3. We have 1 mg, coefficient of 1 times subscript 1, and 1 mg, coefficient of 1 times subscript 1. I'm going to continue to do bookkeeping, but I would encourage you to try to balance these without doing bookkeeping first. And if you get into a snag and you can't do it, then go back and do the bookkeeping. Same thing with using parentheses and writing in the ones. Okay, so we have 2 ClO3s here and 3 ClO3s there. So here's an example of my hint 2 and 3 make 6. What times 2 is going to be 6? Well, let's put a 3 coefficient there. So now we have 3 Mgs and 6 ClO3s. Let's fix the Mgs. It's very important that when you change something that you've counted, go and fix it before you continue on with more changes. So 3 Mgs, let's put a 3 here, so we have 3 Mgs. And then we have 3 times 2 is 6 ClO3s. Let's put a 2 in front of this. 2 times 3 is 6 ClO3s. Now I realize I changed the aluminum, but we haven't counted that yet, so we'll get to it. So we have 3 Mgs, 3 Mgs. 3 times 2 is 6 ClO3s. 2 times 3 is 6 ClO3s. All right, let's move on. We have 2 ALs on the left, right? Coefficient of 1 times subscript of 2. And 2 ALs on the right, coefficient of 2 times unwritten subscript of 1. So we have 2 ALs and 2 ALs. And now for the SO4s. We have 3 SO4s on the left, coefficient of 1, unwritten, times 3 is 3 SO4s. And on the right we have 3 times, now be careful, a lot of times students would tell me that we have 12 SO4s there. That's actually not correct. 3 times 1 is 3 SO4s. So maybe writing in the ones and the parentheses is useful to prevent simple mistakes like that until you have enough practice counting atoms so that you can do that more quickly and accurately. All right, so we have 3 Mgs, 3 Mgs, 6 ClO3s, 2 times 3 is 6 ClO3s, 2 ALs, 2 ALs, 3 SO4s, and 3 SO4s. Always a good idea to go back and check your work after you've balanced an equation because these can be complex sometimes. Sometimes the problems that look complex are not, and sometimes the problems that look easy are complex. All right, here we go, number 4. Notice that NO3 stays together throughout this reaction. There's no other NO things going on here on the right. So I'm going to put parentheses around NO3. All right, let's start with the H's. We have 1 H on the left and 1 2 H's on the right. So let's put a 2 in front of that. So now we have 2 H's and 2 H's. Notice we have 2 times 1, so 2 NO3s on the left, and 1 times 2, 2 NO3s on the right. NO3 is nitrate. And we have 1 Ca on the left and 1 Ca on the right. Notice that CO3 does not remain CO3 over here. It breaks up. So we have to count the C's and the O's separately. So let's count the C's. coefficient of 1 times subscript of 1 means 1C. And there's no other C's on the left. There's CA's, but we counted CA's. And then on the right, we have 1 times 1, so we have 1C. And now on the left, we have 1 times 3 is 3 O's. And be careful, we counted the O's in NO3 already here and here. So we're just going to count the O's that we haven't counted yet. So we're going to count O's here and here and here. So 3 O's here on the left. And on the right, we have 1 times 2, that's 2 O's. And 1 times 1 is 1 O. So 2 and 1 is 3. We have 3 O's on both sides. It looks like it's balanced. 2 H's, 2 NO3's, 1 Ca, 1 C, 3 O's, 3 O's. Problems like this can be problematic if you don't count correctly, so it's very important that you take the time and count correctly. Let's move on to the next example, number 5. Sometimes balancing equations is pretty easy, and here's a good example. We have 2 ALs on the left. We can put a 2 here, so we have 2 ALs on the right. Now notice that if you put Al2, that would be incorrect. Al is not one of the 7 diatomic elements. Remember, you can never change subscripts. You can only change coefficients. So we have 2 Al atoms rather than 1 Al2 molecule. Okay, so 2 Als, 3 O's on the left, and 2 O's on the right. So let's make 6 on both sides. So if we put a 2 in front of that and a 3 in front of that, that'll give us 6 O's and 6 O's. Now be careful, we change the ALs. We now have 2 times 2, 4 ALs on the left. We need to go back over here and change this coefficient so that it's a 4. So we have 2 times 2 is 4 ALs, 4 times 1 is 4 ALs, 2 times 3 is 6 O's, 3 times 2 is 6 O's. Here's another example, number 6. Be careful about your penmanship when you write these out. There's a difference between a little o, that's part of CO for cobalt, and a big O that represents oxygen, or the O2 minus ion. All right, so we have 1 CO on the left and 1 CO on the right, 1 big O on the left and 2 big O's on the right. So we're going to put a 2 in front of this thing. So now let's just do some bookkeeping here. We have 2 COs, and let's put a 2 in front of this, so we have 2 COs. And then 2 times 1 is 2 O's, and 1 times 2 is 2 O's. Notice writing that 1 coefficient in there. Right now we have 1 times 2, that's 2 I's. That's iodine, that's a diatomic molecule. And 2 times 2 is 4 I's. So 4 I atoms when we have 2 times 2. So we need to make the I atoms equal, and we're going to do that by changing this coefficient. What times 2 equals 4? Well, you have to put a 2 there. So that would make 4I and 4I atoms on both sides. And now we have a balanced equation. 2 COs, 2 COs, 2 big O's, 2 big O's, 4 I's, 4 I's. Let's take a look at example number 7 from that review sheet. 1 Fe, 1 Fe, 3 Brs. We're going to put a 3 here, so we have 3 Brs. 3 Cus, 3 Cus, 1 PO4, 1 PO4. Now, if it helps you to count that correctly, to put the parentheses in, to put the 1s in, including the coefficients, then go ahead and do that. So 1 times 1 is 1 Fe, 1 times 1 is 1 Fe, 1 times 3 is 3 Brs, 3 times 1 is 3 Brs, 1 times 3 is 3 Cus, 3 times 1 is 3 Cus, 1 times 1 is 1 PO4, 1 times 1 is 1 PO4. Use whatever hints, whatever techniques that allow you to do the problem correctly, and if you can get away without using those hints, then go ahead and do that too. Now here's an example of a problem that, this is number 8, that looks relatively easy on the surface. I mean, we only have 3 elements, right? We have N and H and O. But it's actually one of the hardest problems on that review sheet. Let's go through this. 1N and 1N. Now I know that I'm going to have to do some bookkeeping here because I know this is a hard problem. 3 H's and 2 H's. Right? Coefficient of 1 times the subscript of 1, and coefficient of 1 times the subscript of 1 again, that's 2 H's altogether. Well, the H's aren't equal. Let's do something about that. We have 3 on one side, 2 on the other. We can make 6 on both sides. If I change this coefficient to a 3, 3 times 1 and 3 times 1 add up to be 6 H's. And I can change this coefficient so that 2 times 3 makes 6 H's. Now notice that we changed the N's. Again, if you change something that you've already counted, go back and fix it. So we have 2 N's. Let's fix that. Let's put a 2 here so we have 2 N's. So 2 N's, 2 N's, 6 H's, 6 H's. We have 2 O's on the left. Anytime we have elements like oxygen here spread out, I'm going to do bookkeeping in a problem like that. And we have 3 times 1, that's 3 O's here, and 2 times 2, that's 4 O's there. That's 7 O's altogether. Now we've run into this problem before. We have an odd number of oxygens on the right, 3 plus 4, you have to add these, right? 3 plus 4 is 7 O's on the right, and 1 times 2 is 2, that's 2 O's on the left. So what coefficient can I put here when multiplied by 2 would equal 7? Well, no whole number, and we need to represent a ratio of coefficients, the lowest whole number ratio of coefficients when we have a balanced equation. So in order to get rid of this odd number of oxygens, or change the odd number of oxygens on the right so that it's even, we're just going to double the recipe. We're going to go through and double all of the coefficients we currently have. We're going to make the 2 into a 4 in front of NH3. We're going to make the 3 into a 6 in front of the HOH. And we're going to make a 2 into a 4 in front of the NO2. So that's what I mean when I say double the recipe. Let's make it so that we have twice as much of everything. And if we double 7 oxygens, that should be 14. Let's go through and recount everything and adjust it. 4 times 1 is now 4 N's. And 4 times 1 is now 4 N's. 4 times 3 is 12 H's. 6 times 1 and 6 times 1 again makes 12 H's. 6 times 1 is 6 times 1 is 6 O's, and 4 times 2 is 8 O's. So now 6 and 8 makes 14 O's combined on the right side. So on the left-hand side, we have to have 14 O's. So if we put a 7 here, 7 times 2 is 14 O's, we now have a balanced equation. 4 times 1 is 4 N's, 4 times 1 is 4 N's. 4 times 3 is 12 H's, 6 times 1 and 6 times 1 adds up to be 12 H's. 7 times 2 is 14 O's, 6 times 1 is 6 O's, 4 times 2 is 8 O's, that's 14 O's. Now, by no means do you have to follow that very specific pathway to get to the correct coefficients of 4, 7, 6, and 4. You can do this many, many different ways. This is really just trial and error. But using the hints can sometimes lead you on a short path to get to the answer. Now, once again, if you have this balanced with coefficients that are twice as big as these, well, technically, all of the elements will be in equal number on both sides. The equation will be incorrectly balanced unless it has the lowest ratio of coefficients. So it should be 4, 7, 6, and 4. Okay, let's take a look at another tricky one, number 9. Here we have NO3 on the left, and we have NO3 on the right, but then we have some other NO stuff going on here that's not NO3. Well, that means that we're going to have to count the N's and the O's separately. Unfortunately, that means a lot of counting. Well, let's get to it. So we have 1 times 1, that's 1 H on the left, and 1 times 1 and 1 times 1 again, that's 2 H's on the right. So right off the bat, the H's are not balanced out. Let's go ahead and put a 2 coefficient in front of this. So now we'll have 2 H's on the left and 2 H's on the right. Let's move on to the N's, and we've identified that we have to count the N's separately because they're all spread out here. So 2 times 1 is 2 N's on the left. And on the right-hand side, 1 times 2 is 2. 2 times 1 is 2 N's from the BaNO3 taken twice, barium nitrate. And 1 times 1 is 1 more N from the NO2 nitrogen dioxide. So that gives us a total of 2 plus 1, or 3 N's on the right. We have 2 N's on the left and 3 N's on the right. Now in the past we said if you have 2 and 3 make 6. Let's go ahead and try that. I want to make the point, when we had a 1 coefficient here, this equation was not balanced. Now that we have a 2 coefficient here, this equation is still not balanced. So let's make 6 on both sides for the N's. And we can do that by changing this coefficient to a 6. That'll make 6 times 1, 6 N's. And by the way, 6 times 1 is 6 H's as well. We have to fix those H's. Let's get on these N's here. So 6 times 1 is 6 N's. And if we double 3, if we make this into a 2, and if we make this into a 2, 2 times 2 is 4, 4 times 1 is 4 N's, and 2 times 1 is 2 N's. That makes 6 N's. We had 3 and we doubled everything, so now we have 6, and we have 6 here. All right, let's fix our H's. We have 6 H's here. To make 6 H's over here, what times 1 and 1 again would make 6? Well, we have to make that into a 3, don't we? So if we put a 3 here, 3 times 1 and 3 times 1 again makes 6 H's. All right, so we have the H's balanced. We have the N's balanced. Let's move on to the O's. 6 times 3 is 18 O's. 3 times 1 is 3 O's. We have some O's here. 2 times 2 is 4. 4 times 3 is 12 O's. Let's count that again. 2 coefficient times 2 outside parentheses is 4. 4 times 3 is 12. So 12 O's from the barium nitrate. And 2 times 2 is 4 more O's from the nitrogen dioxide. So this totals out to be 3 plus 12 is 15. 15 plus 4 is 19. Unfortunately, 19 O's doesn't equal 18 O's. It seemed like the path that we were on was a really good, nice path, but it led us in the wrong direction. Now we could continue on, but when you get that many changes to a reaction, I think, or to a balanced equation, I think it might be beneficial just to go ahead and scrap this and start over. So you can erase everything, but just to speed it up here on the video, let's start this over. This is that same problem. And let's try to not repeat the path that we were on. Let's try to do something different. Now that's really, really important to speeding up your problems. So here we have 1 H and 2 H's. So if we put a 2 there, well, we already tried to balance that before with a 2. I don't want to do that. Now if I put a 3 there, then I'll have 3 H's and 2 A's. I don't want to make 6, and we already tried to put a 6 there. So it doesn't work with a 1, and we tried a 2, and 3 is not going to go. Let's try a 4. You know why? Because we haven't tried that before. And this is what I'm talking about in being creative. Be persistent. Remember the mistakes that, that you've tried that did not work, or the paths that you tried that did not work, and be creative and try something new. So we have 4 H's here. If we put a 2 here, 2 times 1 and 2 times 1 again, 2 times 1 again, that will make 2 times 1 and 2 times 1 makes 4 H's. So we have 4 H's and 4 H's. All right, so now to the N's. We have 4 N's over here. Now, there's some N in this compound and some N in this compound. So 1 times 2 is 2. 2 times 1 is still 2. So 2 N's. And 1 times 1 is 1 N. Now, what can I do to make 4 N's on the right side? Well, putting a number here times 2 is always going to give me an even value. So if I do 2 times 2 is 4, 4 times 1 is 4, 4 plus 1 is 5 N's. Changing that will be too big. Let's try changing this. Let's make this into a 2. So 2 times 1 is now 2 N's. All right, so we have 4 H's. 2 times 1 and 2 times 1, that's 4 H's. 4 times 1 is 4 N's. And 1 times 2 is 2. 2 times 1 is 2 N's. 2 times 2, or rather 2 times 1 is 2 N's. So 2 N's and 2 N's is 4 N's. All right, 1 times 2 is 2. 2 times 1 is 2 N's. 2 times 1 is 2 N's. That's 4 N's. All right, 4 times 3 is 12 O's. 2 times 1 is 2 O's. 1 times 2 is 2. 2 times 3 is 6 O's. 2 times 2 is 4 O's. So 2 and 6 is 8. We're going to add these. Add 4 more. So 2 plus 6 is 8. 8 plus 4 is 12. Hey, 12 O's and 12 O's. It's balanced. So we have taken a look at the H's and the N's and the O's. Now about the BA's. We have 1 BA on the left and 1 BA on the right. Looks like we have a balanced equation. And just like a jigsaw puzzle, when the pieces begin to fit, they can all fall in place and it can go just that fast. So by being a little creative, putting a 4 here, because for no other reason that we haven't tried it before, that allowed us to, with some good bookkeeping and correct counting, that allowed us to balance this equation relatively easily. So 4 times 1 is 4 H's. 2 times 1 and 2 times 1 again is 4 H's. 4 times 1 is 4 N's. 1 times 2 is 2. 2 times 1 is 2 N's. 2 times 1 is 2 N's. So 2 N's plus 2 N's is 4 N's. 4 times 3 is 12 O's. 2 times 1 is 2 O's. 1 times 2 is 2. 2 times 3 is 6. 6 O's. 2 times 2 is 4 O's. 2 plus 6 plus 4 is 12 O's. 12 O's and 12 O's. And then 1 BA, 1 BA. That's about as tricky as you could expect something to be. And sometimes, like I said, problems will appear to be not so hard, and then it turns out, boy, that was kind of tricky. And here's another example of that. Again, we only have 3 elements, C and O and AU. Carbon, oxygen, and AU is gold. But this is kind of a tricky one to balance. Let's go through this. We have 1 C and 1 C. Now, I have oxygens that are spread out here, so I'm going to make sure I do some bookkeeping. Anytime elements like oxygen or any other elements that are spread out like that, make sure you do bookkeeping. All right, 1 times 2 is 2 O's. 1 times 1 is 1 O. And 1 times 3, that's 3 more O's. So we have a total of 4 O's over here. Well, we have 2 on this side and 4 on this side. Let's go ahead and change this coefficient and make it into a 2. So 2 times 2 is now 4 O's. And we have 4 O's. And now we have 2 C's. We have to fix that. So we put a 2 there. And we need to change that. So now we have 2 C's. And, well, we need to change this coefficient and make it a 2. So now we have 2 C's and 2 C's. 2 times 2 is 4 O's, and 2 times 1 is 2 O's, and 1 times 3 is 3 O's. Well, now we have 5 O's on the right. Well, we tried balancing this with a 1 here, and we tried balancing this with a 2 here. We haven't tried a 3 yet, so let's go back to the drawing board and start balancing this with a 3. So if we put a 3 here, that'll give us 3 C's And then we'll need a 3 here so that we have 3 C's. And then 3 times 2 is 6 O's. And 3 times 1 is 3 O's. And 1 times 3 is 3 O's. Hey, that's 6 O's. 6 O's and 6 O's. That balances it. Then we have 1 AU and 2 AUs, so we can put a 2 coefficient and make that 2 AUs. And we have 2 AUs. So it's now a balanced equation. So again, by being a little creative, trying something we haven't tried before by putting a 3 here, we can make this what was kind of a tricky problem not so tricky at all. This is now balanced. So be creative, use a pencil because you're going to probably erase, and be diligent. If you run into a problem that you can't balance right off the bat, that's okay. Skip it, come back, and try to balance it later. Now, if you understand how to balance equations, you should be able to balance these equations. Good luck.